Good morning everybody and welcome to our course on Introduction to Micromechanical Machining Processes. In the last class we have seen the introduction related to the different aspect of the micro machining process, classification of the micro machining operations with respect to other processes, comparison between the different processes like MEMS based processes and the precision machining processes. We have also seen that what things you have to taken care when you are working with a micro scale, that means what are the habits you have to understand, that what things will happen when you operate a micro machine and the macro machine. So, development or the creativity of those type of things will create a good things about the processes. Now, we are going to the next part of the course, that is called scaling laws. So, this scaling law will tell you about the difference between the system at a bigger scale and what parameter affects those system when it is bigger scale, and when you scale down those system to a smaller scale, what will happen, that means what things you have to taken care at that location. So, let us understand those things in the next lecture. So, why scaling law is required? Now, see that there are many components. There are two examples we have given. One is the memory storage, that means if you see long time before, the size of the pen drive was very large, and now if you see at this particular location, now what was the problem here, this large size and small storage, not small, but let us write the less storage. Less storage capacity. But if you see here, it is a small size and large storage capacity. So, this is exactly reverse. Now, when you are moving to this dimension without actually compromising with the storage, but rather you are increasing the storage capacity. So, something we have to do with the component or the system which we are putting inside it. Now, second example is the cell phone. Now, if you see the size of the cell phone or mobile phone long time before, and now if you see it is ultra thin, ultra lightweight, and there are lot of operation which is like a palm top or something, you can do everything which you are doing in laptop or the desktop computer. So, these things are very important to understand that how these things is working. So, what is the present demand, that we are doing a miniaturization of the compact products, and then we are increasing the functionality also. So, once you do both the things, that you are minimizing the size also, but you are increasing the functionality, then we have to think about the what processes will be used for making these products effectively and usable. So, to do this thing or to find out that what things should be done, then to reach to this location, what we have to do? We have to individually components should be reduced in the size and packed. So, now here in this particular case, now there are memory storage available. So, there will be chip available, but the size of the chip will be very small in this case. So, there are small components, and the whole thing should be packed in a small size, 1 centimeter by 1 centimeter also sometimes, and that means we have to put all the components packed with a reduced size. So, that is what is important in this case. So, some system cannot be scaled down favorably, some cannot at all. But now, question is that what we have to do in this particular case. So, here by luckily everything happened very favorably, that everything you can scale down the size also, you can increase the functionality also. Here also it happened very fast, but if you see the machine, that you cannot scale down the machine like a big milling machine to a small milling machine, because there are lot of issues available. These things are movable components. Here most of the things are static components, that means there are no movable part. Most of the things is done by electronic signal. So, that is the advantage of scaling down the electronic system, but when you scale down mechanical system, there are lot of problems. Gravity is issue, inertia is issue, then momentum, the way you are moving components here and there, those things are creating problem. So, we have to find out the which will scale down favorably, which will not scale down favorably, and which some system cannot scale down at all. That means, there are some problems which are very serious, that you cannot move ahead in that particular direction. So, what is scaling? The scaling law becomes important to understand the behavior of the structure or the system when it is miniaturized. So, these are the example we have taken related to the electronics component, but we will focus on to the mechanical part, that what will happen when you scale down one particular car. Suppose you are scaled down a big size car to a small size car, consider a size of the car which is the size of this particular pen. So, now what you have to do? You have to shrink the engine also, you have to shrink wheel also, you have to shrink all the electronics connection, you have to shrink all the related components. So, which particular component will work favorably, which will not work favorably. So, those things will be understood by scaling law of the different system and the different components. So, now there are different ways of doing scaling down. The first thing is, suppose we will consider this Rubik cube, the same size component and the same size, but the more component. Now see the size of the component is same, but instead of this 4 or 5 components, we are adding more components. And if you continue in this direction, what we are doing, that we are adding more and more component, but we are keeping the size same. Now consider this particular milling machine. Now this is the one milling machine, size you consider, it is on an average it is 1 feet by 1 feet or 1 feet. So, this is the milling machine. Can you get all the operation by this machine which can be done on the big size milling machine? So, here what we are doing, that we are scaling down the component, but that this example is not exactly this one. Here what we are telling, that suppose you have one milling machine, let us draw a small schematic here, right. So, this is the conventional milling machine, this is the size. Conventional milling machine. Now, let us not change the size, keep the size same, but we add some components which are useful to improve the efficiency of the component. So, we are adding sensors for tool and machine monitoring, right. Now, we know this machine is completely full, we do not have space and we are adding more component inside it. So, what we have to do this thing, we have to shrink or reduce the size of the machine component, then only we can add something extra. Let us go further inside it, size remains same, let us see the size, let us see volume 1, volume 2, volume 3, V1 equal to V2 equal to V3, we are not changing the size. Now, we are adding sensor here, now we are adding here, other than that we are adding camera plus additional spindle, high speed spindle, in that way we are continuously adding one by one small component, and that means that size is not changing, the total volume is not changing, but we are adding more and more component in that. So, now if you see this particular component, this is the one component, and at this particular location this is the same component at this location. So, we have to reduce the size of the individual component, so that we can add more and more component inside it. So, this is the one way, the size remains same, but we are adding more and more component. So, another thing is the size is small size and the same components. Now, what does it mean? Now, again the same thing is here. Now, what we are doing, that we are not adding more component, but we are just reducing the size of that component. Whatever is here, that remains 4, but the size is reduced here. So, this is what is happening, and this is the exactly the example of this part. So, same milling machine is there, we have not added anything extra here, but what we have done, we have shrink the all the components of the milling machine to a smaller scale. So, this is what is happening in this particular case. And there is one more category, that is what is happening nowadays, the small size and the more components. So, this is the same thing here, but what is happening here? Here the size volume was the constant, but we are adding more and more components. Here we are not adding any components, but we are reducing the size of the components. Now, if you get the both the things in a single part, so what we have to do? We have to add more components here, and we have to find out small size also. So, this is what is happening in the electronics item, that we have seen the earlier example, the pen drive and the mobile phone, that we are reducing the size also, we are adding more component also. So, can we do the same thing in the machining part? So, that is the questions here. So, this is what is happening here, the size of this particular thing is also very reducing. So, it is here, here and here, and if you see one component, this particular component is also reducing from size to size. So, this all the things will create a lot of problem in manufacturing, because just by showing a Rubik cube and changing the size, it is very easy, but when it comes to the actual operation and how to make this component, now if you consider this is the size of a milling machine. So, here if you see this particular component, that means there is a limitation of the size of the component which you can machine, but that is not a big issue here, because anyhow we are going to machine as micro scale. So, when you do this thing, now you consider this is the motor available here, this is the x and y motion, and this is the rotation of the z around the axis, that is called a axis. So, everything you have to encompass in a 1 feet by 1 feet by 1 feet. So, size of the motor, size of the linear scale, size of the travel also, everything is reduced to a smaller scale. So, in that case we have to find out a solution by which you can manufacture this component. Assembly is the next step, but first thing is the how to fabricate this component without compromising the speed, feed and depth of cut limitation of the machining operation. So, what is happening that as the scale of the system reduces, different phenomena or parameter become important. Different phenomena become significant at different scale and other becomes less effective. Now, what happens? What does it mean? That suppose your system is this. Now, suppose here parameter ABC is important. Let us consider any parameter. Now, if you keep the size constant, but if you add more component, this may not be useful. Here something D, E and F parameter becomes significant. If you further reduce something here X, Y, Z important. So, as the scale difference or scale down, different parameter play different role at a different scale. So, it may not be the same scale. Suppose gravity is important at a bigger size, but if you see the gravity at smaller scale, we will see some examples there, it does not make any difference, right. So, these are the important things. The scaling law will tell us that which parameter will affect which way in a different systems. Now, what are the now scaling law at small scale? Small scale means when you are talking about dimensions of hundreds of micron or something, what things are less effective? Gravitational forces are less effective. Inertial forces, that means whatever the weight is there, that is less effective. So, this is the we have to understand how this thing will behave, and when what is more effective, van der Waals forces, electrostatic forces, surface tension, those things will affect very large. We will see that why this thing will effective more compared to the gravitational and all these forces. So, scaling laws are proportionality relation of any parameter associated with an object or system when it is a length scale. Length scale means suppose we have one right. So, here what we will see that this all size are, let us consider A and A, and this is one full system, workable system. Now, this is A equal to 10 and A equal to 0.1. So, if it is a 0.1, all side will shrink to a one particular component, then what is going to happen when this thing will happen. So, everything is related to the length scale. We are not talking about anything other than that. What will happen if you change the dimension of any system? So, if your car is 4 meter long, let us shrink it to the 1 meter or let us shrink it to the 1 foot also. So, in that case what you have to understand, that is everything related to the length scale, not related to any other parameter. If you change the length scale, how this different phenomena will emerge as an important parameter at a different scale, that we will see by looking at the different examples. Right? What are the types of scaling law? So, one is related to scaling of physical size of the object. Physical size of the object means it is a geometry. So, suppose what we have seen, that this is the workpiece with a diameter of d equal to 10 and this is the diameter of d equal to 1. So, this is called scaling, geometrical scaling. We do not see anything other than that, very easy to understand. And another thing is related to the scaling of a phenomenological behavior of an object or a machine. So, what these things are? This is the physical size, again same thing will come out, but material characteristics also important. So, now how this thing will happen? Now, suppose you have one block of a material, any material, and this size is consider a 20 centimeter, right? It is a very big size component. Now, each and every material has some defects. Now, if you take a small portion, suppose these are the defects, so let us name is a defects, right. You take out a very small component out of it, and now see the defect level. Now, if the defect level is something here, it may not be the same thing here, because if the size reduces, the number of defects or number of dislocation, porosity or anything, it will also reduce. So, behavior of material will reduce or it will change when you scale down to some limit. So, this is related to material characteristics, how material will behave when you scale down the component, not related to the other parts. So, these are the two different ways you can actually find out the scaling law, or you can understand the scaling law. One is by geometry, another one is the physical size is also geometry, but addition to that it will also couple the material characterization of the different properties. Now, scaling factor. Now, scaling factor means here what we are considering only length scale. So, whatever parameter we are talking, we have to convert those parameter into the length scale. So, suppose you are considering a volume. So, volume has a length raised to 3. So, it will scale as a length raised to 3, it is a length of the cube of the length. If it is a area, then it is a pi d square. So, it is a square parameter. So, length or the dimension is related to the square. So, in that way there are different parameters, we will see what are these parameters and how we can understand those things. So, let us consider one cube, it has a one length, side is a L. So, we are considering all the things as a one length. So, perimeter is a L. So, it will behave as a L. L means this is the L. So, let me write it here, so it will be clear. So, perimeter is always given by a L, because perimeter, suppose circular is there, the perimeter is the pi d. So, it has a one length scale only. So, that is the way we can understand. Area has a pi d square. So, it has a d is a 1 square is to it, pi d square by 4 or pi r square. So, it is a square parameter. So, it will actually scale as a L raised to square. Now, it has a volume. So, volume has a 3 side, L here and the lengthwise also. So, it has a 3 parameter. So, it will scale down, scale up as a L raised to cube. Now, the mass. So, mass we know, or weight we know, it is rho into V, but rho is not a length scale parameter, but V is a length scale parameter because it is a volume. So, once it is considered as a volume, then what we consider, whatever is here, that will be same as this. So, mass or the weight also scale as a L raised to cube. Then the surface tension. Now, surface tension is the coefficient of surface tension, 1 minute, and the weight perimeter area. So, this weight perimeter area, that is again going in this location. So, it will scale as a L, but coefficient has no any connection with the length scale. Now, moment of inertia, it is a m into r square, and this W we are considering from here, and r square is also radius. So, it is considered as a length scale. So, L cube will come from here. So, this is the L cube and r will be the L square, and this both things will be considered as a L raised to 5. So, this is the way we can consider the different parameters of the resistance. Is also one parameter. Resistance is given by the rho into L by A. So, this is the resistivity, this is the length scale. So, it will be L. So, because L is L, nothing is there. This will be area. So, it will be square as a L square. So, it is a L by L square, and that is the reason it will be scaled as a L raised to minus 1. Right. So, there are different, we are considering only small very less parameter, but you can convert any parameter into length scale by means of their equation, the which way they are behaving. Based on equation, if you find any parameter or any component which is connected with the length, then you convert into the length scale, and then you find out whether it is moving in a positive manner or it is moving in a negative manner. And there are many. So, now how it will happen that now you have relation of all this physical parameter in terms of the length scale. Now, knowing the scaling of a physical phenomena as a power of L, it will guides us to understanding the how design a small mechanical system. Now, if you see that if you are changing the volume parameter, and if you find volume as a one of the parameters of any system, it will be scaled down at a power of 3. If you consider the parameter is a one of the parameters of any system or any equation, but it will scale down as a power of L only. So, when you reduce the system with a parameter, it will scale down very slowly. But if you scale down any system where volume is present, it will scale down very drastically, because it will reduce as a power of 3, not the power of 1. So, let us see some of the example, real living example as well as the man-made examples. So, first thing is the surface to volume ratio. So, this is very important to understand, because we have many components in the MEMS part also, as well as the other components related to the micro machining operation, where we will understand where the surface to volume ratio is very important to understand. So, generally we can tell the smaller things are less affected by volume dependent phenomena such as mass and inertia. We have seen a very small creature also, ant is also there, and small insects are there. So, those are where very less affected by the mass and inertia, and more affected by the area, surface area dependent phenomena such as contact forces and the heat transfer. So, let us see some of the example that how this thing is doing. So, main driving force of all the components, whether it is in MEMS part or it is a micro machining parts, surface to volume ratio is very important to understand, and it will give you the very scientific reason for understanding of something. So, let us take this example. So, here this is one cube, it has a dimension of a L side, and now what is the surface area? Surface area we can understand 6 into A square, and volume is A raised to cube, right. Now, let us consider one dimension of the A. So, let us consider A as a 10 right now. So, 10 may be micron also, millimeter also, or it can be a meter scale also. So, now if you consider A as a 10, you put 10 here, so S becomes 600, and if you put A equal to 10, V become 1000. Now, let us take the ratio of surface to volume. So, if you divide 600 by 1000, you are end up with a 0.6, correct. Now, let us reduce that size now. So, now A is a 0.1. So, how much we have reduced? We have reduced 100. Then if it is a 0.1, now S becomes 0.06. You put the 0.1 here in this equation, you will get this value, and then V becomes 0.001. So, in this particular case, now let us take the surface to volume ratio here, now it is a 60, right. So, now what is important here? Now, surface to volume difference is 6, here it is a 0.6 and here it is a 60. So, now difference is a 100. So, where it is making difference? What is signification? Significance is the heat storage by the volume. So, this is the one of the parameters. So, heat storage is the function of a surface. Heat storage is a function of the part. So, no, note this, 1 minute. So, heat storage is a function of a volume, that how much heat you can store is a function of volume, and heat dissipation is a function of the surface area, right. So, here is the surface area. So, now how this thing will happen, that suppose you have one cube here and here the difference is that suppose you are reducing the size of this cube, you are reducing the size of the cube somewhere here. This much you are doing. So, what we are doing? We are reducing the area, this volume will reduce very drastically, but surface area will not scale down that much way, because it is moving, it is reducing as a a raised to square, while it is reducing as a raised to cube. So, what happened, that smaller cube has 100 times more heat dissipation per unit volume, because here what happens here, now you can see here the difference between this and this is how much? It is 600 from 20 here, let us take 40, this much is the difference, but here difference is a 1, 1, 2, 3, 4, 5 and 6 0. So, this much is the difference when you scale down one particular system worth a 100 of a scale. So, here reduction in volume is very large, but reduction in the surface area is less. So, your storage is very less, but your dissipation is very high. So, if you heat one component with the same temperature, suppose your starting temperature is 100 degree of A equal to 0.1 object and A equal to 10 object. Now, what will happen? Then you put both the things in the same environment and then see the which one will cool down fast. Then what will happen? This particular thing will cools down 100 times faster than this one. So, that is important. Even heating is also that thing, it is not cooling down. If you want to heat, it will heat down 100 times faster than that. So, in this way you have to understand that what will happen when you do machining with a micro scale. Now, suppose you are considering this, you have scaled down the full machine to a micro scale, that we have seen one example, that whole machine is in a 1 foot by 1 foot by 1 foot. Now, you are doing physical contact, that means tool is in contact with the surface, it will do friction, it will generate heat also, and it will many heat will be carried out by the chip, and chip is fallen down onto the base. So, when it is fallen down on the base, at that time if this thing is playing important role, what is going to happen, that particular localized area will be heated very fast, because the area is small, area is large, but volume is small. So, when there is a heat, at that time there is a one particular parameter, it is called coefficient of thermal expansion. That particular material will expand, let it be at micro scale, but it will also degrade the total loop of the, what is called stiffness loop of the machine, and ultimately you are end up with the wrong size of the component. So, this is one of the example by which it will create a important role in this particular part. Now, another example is the weight versus surface tension. Now, you consider the when you fill a one glass with a water and overturn the glass, all the thing will spill away, because nothing will be stick there in that case. But if you see same thing at a micro scale, now if you put a water into the capillary tube, it is very tricky that even if you put it down, means upside down, then water will not spill out very easily in this, because that will happen because of the size scale. So, what is happening here in this case? Because here the surface tension and the weight will create a important role here, because we know that whatever the weight is actually scaling as a L raised to cube, but the surface tension, that means whatever is this particular part is here, that cohesiveness of the particular water molecule, that will scale as a L square, L only. So, when you are scaling down from here, suppose here it is a 1 centimeter by 1 centimeter by 1 centimeter of water, and that will come down as a 10 micron cube, then it will be very small in this case. So, here the weight, whatever is weight here, that weight will be reduced as a L raised to cube, but the surface tension will reduce as a L raised to 1 only. So, that is the important thing here, that what is happening when it is. So, here it is a very difficult to move. So, you have to pressurize something from the top, and then only it will move from the downwards. Right, the surface, due to surface tension, become predominant at a very small scale. That we will see in some example of the fluid mechanics also. Now, another example with the weight versus surface tension. We know the mass is a function of a rho into V, and V will scale as a L raised to cube, and this will be important in this case. Now, surface tension is this particular parameter. Now, if you have seen that some insect will stay onto the water surface. So, here the surface tension will scale as a perimeter area into surface coefficient, and it will scale as a L, and animal becomes smaller, weight decreases more rapidly than the surface tension. Right. So, surface, suppose consider the example of water. Water has surface tension around 72 millinewton per meter, and if you see at that time, at this location, the bug with a 10 milligram of a weight, it needs only 1 millimeter of footage to walk onto the water. But if you consider man or human, it has weight around 60 kg, then what we need, if you scale down with respect to that, what we need, that we need a feet of a 8,000 meter to walk onto the water. So, that is the way it will behave differently. So, let me finish this lecture here. We will continue with some more examples into the scaling effect of different strength. Thank you very much.